What is up, everybody? Right. Welcome to my channel. And right now, we're gonna take a look into a paper called "Strategies: Learning Strategic Skills by LLMs Using Bi-Level Tree Search." Yeah. This right here is a paper that came out like 2 days ago, I believe. I forgot. It could be a week ago. Um. So what caught my eye about this paper is that it is able to guide the large language models to perform actions that we want it to do via feedback mechanisms. And I thought to myself, it might be a good idea to go through this with you guys, right? So the idea is this. I will be going through this paper section by section, and hopefully we all can understand this uh, together as a team, right? Okay, right. Let's go through the abstract first, right? Okay. In this paper, we propose a new method strategist that utilizes LLMs to acquire new skills for playing multi-agent games via a self-improvement process. Hmm. Sounds kind of similar to Q star, but let's continue. Our method gathers quality feedback using self-play simulations. Right, something like AlphaGo, I think, with Monte Carlo tree search and LLM-based reflection, which can then be used to learn high-level strategic skills such as how to evaluate states that guide the low-level execution. So when they talk about low level execution, I'm just gonna assume like how LLMs are pretty good at planning on the high level, but it kind of sucks at executing the low level actions. So that's what they're trying to fix here. Okay, we showcase how our approach can be used in both action planning and dialogue generation in the context of games. All right. So I'm not so sure what do they meant by games, but we shall see. Probably some kind of like NPCs, maybe I don't know. Achieving good performance on both tasks. Specifically, we demonstrate that our method can help train agents with better performance than traditional RL based approaches. Ah, damn. And other LM based skill learning approaches in games, including the game of pure strategy, GOPS, and the resistance, Avalon. And look, I'm not too sure what these two games are, um, but let's have a look on Google, right? So let's go through that, see if we can find anything about it. Right. So on Google, right, according to Google, GOPS is a simple bidding bluffing game played with an ordinary pack of cards with all the hearts removed. One player takes all the spade cards and the other all the clubs. The diamonds are shuffled and placed face down in the center of the table. Uh, the diamond cards are turned over one by one. Okay. I still don't quite understand uh, what the game is about, but I do assume it has to do with like poker cards as shown on the screen right here. But anyway, let's check out the other game. The Resistance Avalon. I'm not so sure about that either. Let's have a look. Okay, right. So, is this the actual game? Right. So it's a not it's a board game this time. The Resistance Evolon, 2012. Who Can You Trust? A game of social deduction set in King Arthur's legendary realm. I'm not so sure either. Well, okay, let's have a look at Wikipedia. Right. The Resistance is a social role-playing card-based social deduction party game. The premise involves a war between government and resistance groups, and players are assigned various roles related to these groups. A King Arthur theme variant with additional roles is marketed as Avalon. Like other social deduction games, the Resistance and Avalon rely on certain players attempting to disrupt the larger group working together, while the rest of the players work to review the spy working for them. Ah, okay, I see. So, so it's trying to like catch the spy, huh? All right, right. I kind of get it now. Okay, so and that's the gameplay. So the resistance and the spy. But I think the paper will probably go through all the games in a bit more details later. Okay, so now back to the paper, right? So we kind of know what the paper is about from the abstract, but I think what's more important is to see the headings of the paper. So the paper begins with an introduction, as usual, introducing the problems behind and what they are proposing, they are going to solve using, and they are going to show us their methodology with strategic learning and decision making settings, defining the problems, and there's a whole lot of figures and text here. We're going to go through those in a bit more. Let's see, and they also show some experiments. We're going to cover that as well if we have time. And let's see. Right. And they do have some parts about stuff that's related to their work. Right. Let's see. All right. And lastly, they ended it with limitations and conclusion. So what I would probably do right now is we should probably start with the limitations and the conclusion. And for good reason, because usually in the conclusion section, there will probably, uh, I think it's a good summary, a secondary summary of the entire paper, so it would be much easier for us to understand what's going on about the paper. Okay, right. So let us go into their limitations now. While our method performs better on average, right? I'm assuming their method, right? Perform better on average. Individual runs can have high variance. Ah, okay, interesting. Since the performance of an agent in the multi-agent adversarial game settings is highly dependent on the opponent's policies, feedback from these opponents tend to be noisy. Okay, I think that's a really important statement there. So the feedback is noisy. Okay, with noise increasing with the number of players. Ah, I see. So it's kind of like chaotic in the sense that the more agents you have, the more chaotic it becomes. This is especially true when learning Avalon heuristics, where the performance depends on the policies of five other players, teammates, and opponents. We believe that running more game simulations with different opponent policies can help reduce this feedback noise. Okay, so the belief that running more game simulations with different opponent policies can reduce this feedback noise. Look, right. I'm not so sure what they meant by this, but yeah, let's take a note of that first. Okay, we also acknowledge the inherent noisiness in LM generations and how this impact our results. Okay, so they're talking about the noisiness of the LM generations. I'm thinking maybe they are referring to like the the sampling uh, protocols that they use during the LLM inferencing, but we shall see. Okay, we tried to reduce this noise by number one, using the same seed functions when benchmarking the different LM improvement methods. Right, the same seed functions. Okay, setting the seed. Number two, collecting generated strategies from multiple runs. All right. So, okay. We also did not test our method on other non-adversarial environments, such as Q&A and text-based worlds. However, given the strong performance of our model in adversarial multi-agent settings, we believe that similar performance will be observed in single-agent non-adversarial settings. I mean, it should be obvious that if their approach works for the multi-agent setting and it's like noisy and adversarial-ish, I think it would probably work in a single agent setting too, I believe also. All right. So, okay, right. Let's move to the conclusion. In conclusion, we have presented strategies, a new generalizable non-parametric. Why are they saying non-parametric? Okay. Self-improvement framework that learns and improves skills. Given the rules of the game, our method is able to learn good strategies to play the game through self-play without task-specific prompting. Okay, now this is really cool, right? Because like if you have been working with LLMs, there's a lot of things that you need to specify specific prompt in order to make the LLM do what you want. And in this case, they say it doesn't need any kind of like specialized prompting, and I think that would be useful for all of this, right? Okay, and they say or human generated policy data. I guess that makes sense as well since it's LMs. The performance of strategies suggests that incorporating better guidance, whether this be through modular high-level search, okay, modular high-level search or low-level simulated self-feedback into the LM improvement processes can greatly enhance the improvement process. Okay, and that's it. Right, cool. Right. So the entire thing now, just by reading the conclusion and the limitations, we get an idea about what it is. So, yeah, just bear in mind that low level simulated self play, high level search, right? And there's no specific prompting, no policy data. It's non-parametric, and there's something to do with the noisiness of the environment. Apparently, they mentioned that it comes from the LLM generation itself, but let's go through the methods. Then we shall know if that makes sense. So let's go to the methods now. No. How about if we go through the introduction? All right. Yeah. Sorry. All right. Let's see. Okay. Intro. Right. Recent studies have demonstrated how LLMs can be utilized to learn skills for improved decision making in in interactive environments. Right, makes sense. However, learning skills in adversarial environments where multiple agents presents a significant challenge for LLMs. That's the real world. As it requires accounting for the responses of other players or environment for their actions. In these environments, it is hard to determine the optimal policy, since strategies that are effective against one opponent's policy may not work for the other. Let's highlight that. Okay. Moreover, the complexity of these environments means that we need to smartly search across a large policy space to find the optimal policy, right? And I bet that's what they are going to do. Okay. Hence, existing LM self-improvement methods that rely only on the feedback of LM often have trouble distinguishing what improvements help and ended up in local optimal strategies that can be exploited, right? Exploited in the sense of adversarial attacks, something like that. All right. Okay, so in this paper, we study how to, number one, acquire and analyze feedback in these noisy environments, and number two, making sure that the improvements actually help against different opponents. Right. They propose a method called strategies that learns an effective policy. Right. It first learns the effective policy, evaluates the policy in absence of the real environment at a low level, and finds such policy effectively. In other words, we are learning how to learn. Learning how to learn. Uh, I'm not so sure about that though. Oh, wait, hold on. That learns an effective policy, right? It learns a policy, then it evaluates the policy in a fake environment, I guess, and finds the policy. What do you mean by learning how to learn? I don't really understand. But I think they will probably explain it as we go along. Just give me a second. Let me have a cup of water. Hmm. Okay, let's go. Specifically, our approach combines LLM self-improvement with research. Okay, LLM in self-improvement research both on a high-level strategy space or skill space and also on the low-level action space. On the high level, we do this by constructing a strategy tree, right? We do this by constructing a strategy tree in an evolutionary process where we improve upon previously generated strategies. Right, so evolutionary algorithm, something like that, has to do with Monte Carlo tree search in that case, right? In our gameplay settings, we specifically learn a value heuristics, right? Value heuristics to evaluate game states, a dialogue guide to guide the dialogue generation process, right? So they have a bunch of things here, a value heuristics and a dialogue guide to guide the dialogue generation process. During the process, we also learn how to improve strategies and what types of improvements tend to be more helpful generally. We search across the strategy tree using exploration and exploitation methods, eventually finding the good strategies. No parameter updates. Okay, right. I see what they mean by non-parametric in this case, because it's yeah, they don't change the LM parameters. So this is where the term non-parametric comes from. All right, cool. So I mean, in that sense, any kind of like prompting would be non-parametric. So yeah, I mean, I don't think it's necessary to write non-parametric, but whatever. Okay. The strategies are tested out through simulated self-play on the low level. Okay, right. Just like what the conclusion said, right? The low level is about self-play. By mastering a high-level strategy, the LM not only learns a good policy for the player, but also gains insights into how the opponents might react to the policy. Okay, right. With this information, our approach can simulate the behaviors of both players and opponents by Monte Carlo tree search, MCTS, gathering feedback from the simulated trajectories and the search process. Right, and they have a metaphor here. In other words, we leverage the world knowledge in the LLM to simulate behaviors of both the players and the opponents in order to get better feedback and plan better. Okay, so yeah, so that basically sums it up, right? So they use the world knowledge in the LM to simulate behaviors of both players and opponents in order to get better feedback and plan better. This kind of sounds like what is it called? Tree of thoughts, but instead of like having experts, you have like players and opponents in that sense. Yeah. Yeah, maybe not so related. Anyway, yeah, okay. We apply our method to two games, GOPS and Resistance Avalon, and show that our improvement process works for both games with dialogue and games without. Right. We find that our improvement method is better than many other self-improvement methods, including both existing LM-based self-improvement methods and traditional RL training approaches to AI in games, given the same computation and data budget. We also show the effectiveness of our method of collecting simulated self-play feedback using search to provide feedback. Right. Right. To summarize, their main contribution are we propose a general non-parametric LLM skill learning framework in which a low-level self-play tree search. Right. This is right. Okay. Right. Dang it. A low-level self-play tree search. That's three different things in a single phrase. Low-level self-played research provides value feedback, and high-level skill learning module. Right, the functions improves the skill in various forms, including functions and textual strategies. To improve the sample efficiency of skill learning, they introduce a modular search method that factorizes the process by an idea implementation search with bandit exploration. Man, this is really intricate. We applied this framework to GOPS and Avalon and show that learning a value heuristic and dialogue strategy guide, we can learn a good policy for both action planning and dialogue generation. Some examples of good strategies learned through our method are shown in the appendix, I believe, which achieve higher win rates against other agents. Okay, so there's quite a lot of things right here. I'm not so sure if we can actually go through everything since there's like 61 pages. That's really a lot. Okay. Let's see. Okay, let us go through some parts of the methods. Um, right. Okay. But yeah, let's go through that. So, okay, let's go. Methodology. Section 2.1, strategy learning in decision making setting. Okay. The general framework for their approach is shown in Figure 2 and Pseudocode 1. Okay. Uh, let's look at that later. Our improvement contains two improvement steps. Right. So two steps in each improvement cycle. Okay, this is important. Number one, reflection and idea generation step. Okay, reflection and idea generation. And then number two, strategy improvement step. During the idea generation step, we prompt the LM to reflect on simulated self-play feedback. Right. So to reflect. Wait, isn't this kind of like the other paper, the one that came out like 2 years ago? I think it's from Stanford. What is it called? Star, this the bootstrap approach. because no, sorry, yeah, I mean it has some similar parts to it, but not necessarily, because it's this one is about reflecting on the simulated self feedback, while the other one is about reflecting, creating some kind of like reasoning behind the questions that the model gotten wrong. So not necessarily the same. Anyway, yeah. So we prompt the LLM to reflect on simulated self-play feedback from previously evaluated strategies and generate possible improvement ideas. Okay, from previous evaluated strategies and generate possible improvement ideas to the strategies and add them into a queue. Okay, I have to admit, I have this idea about an idea queue um, a, a couple of months ago. Apparently, they caught up, so great, I guess. During the strategy improvement step, we select a strategy from the strategy tree, right? So they select a strategy from the strategy tree and an improvement from the idea queue, and prompt the LLM to improve the strategy using the improvement idea. Huh. Okay, right. Here's the thing, right? I haven't taken a look at the results, but I think this kind of like cycle, it won't improve like the performance infinitely as you go through the cycle. I think there's gonna be a plateau at the end, right? Anyway, the improved strategy is that evaluated using self-place simulations, and we use the feedback and reward signals from the simulation to help guide future improvements. Okay, cool. Now, the general goal in our decision making setting is to learn a good policy function in the sequential decision making setting, generally formulated as a partially observable Markov decision game. POMDG. That's a mouthful. Anyway, let's highlight that. Yeah, which can be done by improving strategies associated with the policy function. We describe in more detail what a strategy looks like, how we derive a policy function from a strategy, and how to acquire feedback for the strategy for both the dialogue generation and the action generation. Okay, there's a lot of information right here. Let's see. We describe in more detail how what a strategy looks like. Okay, right. So let's see. If we come back to the first sentence right here, the goal is to learn a good policy in the sequential decision making settings, which can be done by improving strategies associating with the policy function. We describe in more details what this strategy looks like, how we derive a policy function from the strategy, right? Going from the strategy to the policy function and acquiring feedback for the strategy for both the dialogue generation and the action generation. Okay, that kind of makes sense. Right. Problem definition. Given state space S and action space a policy function, I forgot what this symbol is called. I think it's called phi, I believe. Let's have a look. Phi. Yeah, not quite so. How about psi? Is it psi symbol? Apologies. I'm not really good with symbols. Wait, hold on. It's and anyway, I'm just gonna call it phi. I don't care. Right. A policy function phi in policy space is big phi. It's a mapping. Yeah. So this phi mapping maps the state space to the action space, but there's this right here. This del symbol where we allow phi to output a probability distribution over the actions. Okay, right. So it's something like a softmax. All right, so it's something like a softmax, right? Softmax, and you have like a probability distribution here, and then you pick the most probable one, probably something like that. But we shall see. Right. Okay. Right. To output a probability distribution over the actions. Okay. An environment. I don't know what this is called. I just call it E. Whatever. E equals to a collection of state space, action space, a set of actors, transition function, a reward function, a action function, right? And this phi e, which is the policy function for the environment actor. Yeah, let's see about this. Let's see. Okay, right. Let's go through it. After this, defines the state space as the action space A, set of actors N, a transition function. The transition function maps the the product of S, the state space, and the action space, and maps it to another part of the state space. And a reward function R taking into account of the state space and the action space, and then giving it some kind of a reward value, and it's and the vector size is probably the length of the number of actors, right? Right. And that specifies the intermediate rewards for each actor. An action function A maps the state space to the number of actors. Okay. I don't know why that seems. I'm not so sure. Perhaps you can tell me down in the comments, but maybe this paper will explain more. PA that specifies which actor may take what legal actions at some state where P is power set. Phi E, the policy function for the environment actor. Okay. Note that transitions are deterministic in our notation, and stochastic transitions are handled by the environment actor E instead. So we cover stochastic, deterministic, multi-agent, and single-agent cases. All right. For a partial information setting, we also have a space of information sets I. All right. So for partial information setting, they have a space of information sets I and a function H that maps S and then to the information set space from the that maps from the hidden states and the actors to hidden information sets where phi, hence phi maps the hidden information set to the action distribution. Okay, right. Let's see. Yeah. So let F map sigma to big phi be the function that maps strategies to policy. Right. A high level strategy sigma I think this is called sigma. I forgot. Yeah, a small sigma belonging to a big sigma, right, helps parameterize policies so that we can search over lower dimensions, big sigma space instead of phi. Let phi underscore minus I denote the space of possible opponent policies. Then the goal is to search for this sigma I, this optimal strategy sigma I that approximates finding the optimal policy given the policies, right? So finding the optimal policy given the policies of other agents. Right. That's really interesting. Huh. Hold on, just let me have a sip of water. So now this is really interesting. So so in this equation, finding okay, right. So argmax, right? Argmax. So we want to find this optimal policy that would increase this term right here, this expectation term right here. So we want to find a policy that increases the reward, right? And we can approximate this, right, into this. So what we can do is to find Um, yeah, yeah. So, okay, right. This is the optimal strategy, and now it has become finding the optimal policy given the other agents' policies, right? Such that you can maximize the reward, the expectation of the reward. And tau equals to S sub zero, A sub zero is the simulated trajectory according to the joint policy, and the transition function t with at being sample from I think this is sample sample from the phi at conditioned by st, and st plus 1 equals to the transition of st and at, I think. Okay, right. Let's move on. The state space, action space, and actor space are different depending on the setting. In non-stochastic single agent settings such as Q&A, n equals to 0, right? N equals to 0. Wait a second. But I thought n is the number of A actors, right? Wait, if that's 0, why the hell is it zero? Shouldn't it be 1? Oh well. Anyway, in stochastic single agent settings such as a web shop or classic web shop, um, n equals to minus 1 comma 0, right? So it is that. Wait, minus 1, where we add an environment agent minus 1. Okay, I see. Okay, right. So this n variable isn't necessarily the number of agents. It's the set of agents, right? My bad. Let's see, where's the definition? It should be somewhere here. Yes. My apologies. Yeah, I thought this says 0 actors when it's just an actor that's labeled as 0. Okay, my bad. Okay, right. So to have an environment agent minus 1, we focus on adversarial multi-agent stochastic game such that we have minus 1, the environment agent, 0, the main agent, and 1, blah, 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 blah. Those are the opponents. Right. In non-dialogue based games such as GOPS, for example, S consists of the cards played so far, and that's the set of actors. Wait, the environment, the main agent, and a single opponent, and A consists of the cards that you can play. In dialogue-based games such as Avalon, A consists of both the discrete actions, moves such as voting, and also all possible natural language texts of a given length. Similarly, S consists of both historical moves and historical dialogue record. So that has a lot of actors in it. All right. So let's see. Yeah, skills refer to any high level strategy space where the strategies can be learned. Blah blah blah. Yeah, there's a whole lot of details in this paper, but I think there's in fact too much. How about if we just skim through some of the details, right? Because we don't have much time left. If I have to cover everything, it would probably take me more than 1 hour, which I don't want to do because I have other work to do right now. But yeah, let's see. Okay, right. Let's read this, right? So, okay, right. The framework utilizes LMs without supervision, and the feedback comes from simulated self-play, right? And they have reflection, idea generation step, and strategy improvement step, which we covered before. When improving, we use an adaptive selection process such as upper confidence bound and best first search, right? Best first search. Not so sure what that is, but let's keep on going. Right. So that's the figure right there, but I think we should read this first. Okay, right. So during idea generation step, a strategy sigma and its simulated trajectory feedback, tau sigma, is first selected from the strategy tree according to the adaptive selection process. Adaptive selection policy. The feedback usually trajectorized from previous self-play simulations, including the states that it visited, the actions taken at those states, and the estimate win rate. Okay, right. And the estimate win rate. So there's the X and Y and the final outcome, the trajectory and any intermediate values used during the simulation. Since the trajectories are very long, they select only some of the key states in the trajectory to translate it into natural language. We then prompt the LLM to reflect on this feedback and propose new ideas on how to improve the function. These ideas are added to the idea queue along with a score prior to how good the idea is. During the strategy improvement step, we first select a strategy and an idea from the libraries during the adaptive selection policy. We then prompt the LM to implement the idea of the strategy, generating a new improved strategy. We then evaluate the strategy using an evaluator which conducts self-play simulations with the strategy and records the simulated trajectory data. During simulations, players conduct Monte Carlo tree search. You don't have to repeat this, authors. It's implied in the abbreviation to estimate the expected win rate at different states, which provides additional feedback. We add the improved strategy and its performance to the strategies tree and update the improvement score for the idea that was used. Right. All right. Okay. Let's go through this one. Okay. A key challenge during the improvement process is that it is often difficult to evaluate whether an improved strategy is better than the old one and why. Yeah, I can 100% relate to this because, yeah, it's really hard to evaluate it, especially if you like evaluate it on like a single circumstance and quite often, right, that strategy doesn't just like generalize across every single scenario. So let's see what they have to say. um, Simply querying the LLM to improve the strategy based on the feedback without guidance from an improvement idea often results in making changes to all parts of the strategy. Thus it is hard to determine what changes affected the strategy after we evaluate it. So they use an additional, right, so they create an additional idea queue to modularize the search space. Not sure what that means. Instead of improving everything at all once, we incrementally improve the strategy. And serendip here, okay, right. Uh, what is this? Ceteris, Okay, right. My English isn't that good, right? Oh yes, this one. Sir, ceteris paribus. I swear I seen this word, this phrase, this morning. Anyway, holding other things constant, right? Holding other things constant, creating a more scientific testing and improvement process that avoids confounding factors. I mean, there's a better way to phrase this. Whatever. Um, Moreover, the IDQ helps us track what improvements have been successful in the past, which are also likely to help in the future. Since the strategies are similar and used in the same setting, improvements from one can be transferred to another. These improvements often involving additive adjustments like penalties or extra questions are generalized across strategies. We are specifically prompt for high-level generalizable ideas, right? For example, an improved idea might be to add a question asking the player to assess their level of suspicion to its other players and craft a statement addressing how they interact. In the case of value heuristic generation, an example would be revise the dynamic penalty adjustment to be more accurately reflecting the impact of the higher value scorecards left in the deck. Okay, right. Makes sense. So far, we need to have two separate idea queue, right? So it's kind of like in Python where you have the queue right there, but you have two of them, right? Okay, right. So let's see. Let's go through this quickly. We're running out of time. UCB, upper confidence bound sampling from the idea library help us to improve new improvement ideas and exploit old ones. Okay, right. So this is UCB improvement idea, right? The empirical Z bar empirical average improvement score plus some kind of C term right here. Not so sure what this is. The ln of n total divided by n improvement ideas. Right. So n total is the total number of idea implementations, and n improvement idea is the number of times they have implemented this idea successfully. Right. I see. So let's see. To make the improvement process manageable, we optimize the policy for the dialogue and the moves separately in Avalon. Okay, right. So that's that. We have covered what is this one called right here? Strategy for uh, re high level reasoning. Okay, right. Let's see. Right, and the next part it talks about this right here. Let's see. Yeah, I think we can probably skip some of the parts due to time constraint. I have to go like very soon. But yeah, as you can see right here, if we take a look at the results, it's actually not bad. Um, you see, if we take a look at the scores, just by glancing through the scores, just give the computer 1 second. Right. So obviously, if we take a look right here, their approach is significantly right. Although there's no statistical test right here, but you can obviously see that it has a higher average score compared to RL training. I'm not so sure what kind of RL training they're using. I haven't read it yet, but yeah. I mean, the fact that this outperforms RL is already. I mean, there's a lot of papers that kind of show that you can outperform RL using LLMs, right? So yeah, I mean, it's a really dense paper. Yeah. So let's see, what else should we cover next? I mean, there's a lot of things right here that I would like to go through. But yeah, let's have a look at the figure, right? Yeah, I think this figure is the most important one. Yeah. So okay, yeah, right. So we're gonna end this video off with figure two, overview of skill coach improvement method. There are two improvement steps: idea generation step and strategy improvement steps. We alternate between the two. Okay. So let's start from here on the left, right? Strategy library. So it seems to me that there's a tree of strategies, each idea being the edge. Idea A links between strategy to strategy A, and then idea A links that to that. Okay, and the selected strategy A, B trajectory feedback and priority score. I believe that's what they select using adaptive tree bandit selection policy. Right. Okay, and now we reach key states in simulated trajectories. Um, right. State. Players have said discussion history, blah, 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 so far, and this is in action history. Okay. This is an F string, right? So you have like variables inside the string. So action, the students say blah, blah, blah. Outcome, good, loss, evil, won. Search estimate, 30% win rate. Okay. Intermediate values. The student answered the questionnaire as follows. Question one, answer one. Question two, answer two. Right. So, and you feed this description of the state as follows. You are a coach. Previously, you suggested that this strategy, which produced this intermediate values at this state, search suggests that the value of the state is search estimate, while this is the final outcome. What conclusions can you draw, and what are the the number of ways we can improve this strategy? The strategy, right? So I guess idea generation. Yes. No, not idea generation. This is a strategy improvement step, and then generated ideas. Well, okay, right, ideas. Add a question that asks blah 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 blah. Okay, these are the collection of ideas. You put them into an idea queue, right? And then you alternate between steps. Okay, let's see. Right. So we have this right here, and then okay, right. Berlin top process questionnaire, blah blah, and questions selected. Okay, right. So the main agent has to select a strategy and select an idea, and then we put it into this prompt right here. You are a coach. Previously, you suggested that this strategy. Implement this improvement idea into the strategy as best as you can. And then this happens, right? So you have the improved strategy and you evaluate its outcome. And finally, you update the score of the improvement idea, and then you also update the strategy, I believe, right? And then we go back to the very first step that we started out a few minutes ago. Yeah. Yeah, I can see myself implementing these two steps on my own, right? Obviously, if you ask me, this is quite computationally costly because like there's already multiple steps, right? I I mean, yeah, I mean yeah, it's kind of similar to other ideas that I've gone through before when I was reading paper on my own. But this one is not too bad, not too bad. Yeah. So yeah. Anyway, that's it for now. Yeah, if you have any comments about the paper, please feel free to comment down below. Yeah, if you like what I'm doing here, make sure to like and subscribe. That really helps me out putting out these videos out. And yeah, yeah. So yeah, if this video goes up well, I might do another video for another paper. So yeah, thanks for checking this video out, and I will see you guys in the next one. Bye.